Okay, so in this example, we're trying to find the rotational inertia or the moment of inertia of this system of 4 objects connected by light rods. So we're going to assume that the rods themselves have no mass and that the only masses we need to worry about are the masses of the squares, the cubes of mass m. So you want to imagine almost like in the first part, placing your thumbs at these 2 points on the axis here. Draw little X's on the drawing here. So imagine grabbing the object there and rotating it about that point. That's what we want to know, how difficult basically it is to rotate about that point. So we know that for a system of particles, the moment of inertia is going to be equal to the sum of each mass times r squared. And r in this example is how far away each mass is from the axis. That's what we want to think of it as. So if we're talking about the moment of inertia about the y-axis, in this case, we're going to go the small mass on the left top corner, which is 1.8 kilograms, times how far it is from the axis, which is 0.5 meters. We'll square that, plus the top right mass, which is also 1.8 kilograms, times its distance. And if you look at the picture, it's 1.5 from end to end and 0.5 on the left-hand side, so that's 1 meter on the right-hand side. Then we got the bottom left, which is 3.1 kilograms. Its distance is 0.5 meters. And bottom right, which is 3.1 kilograms, and its distance is 1.0 meters squared. If we do all that, we end up with 6.125 kilogram meters squared. So that's I about the y-axis. Now we'll look about the x-axis. So we use the same idea, but we're going to go using distances from the x-axis in the picture. So again, you want to imagine grabbing the object at these 2 points perhaps with your thumbs and then rotating it around that point. Okay, so the way it's drawn, every single mass is the same distance from this axis. They're all 0.25 meters from that axis. So we have 1.8 kilograms times 0.25 meters plus 1.8 kilograms times 0.25 meters again, plus 3.1 kilograms times 0.25 meters plus 3.1 kilograms times 0.25 meters, and we add all that up. And we end up with 0.6125. Interesting that we get the same numbers, same digits here, but one's 10 times different than the other. So talking about this conceptually a little bit, here's one thing I just want to address for now, just to think about. Imagine trying to find out where the center of mass of this system of 4 objects is. We know that the objects on top are lighter than the objects on the bottom, so we know that the center of mass is going to be below that drawing of the x-axis, that dotted line. It's definitely going to be lower than that. And the mass on the left and the mass on the right are the same. So it's going to be halfway between the left side and the right side. So in other words, the center of mass is probably going to be, just conceptually speaking, somewhere is about here. So let's call that the center of mass. Okay, now, if you look, we can see that our dotted line for the x-axis is closer to the center of mass than the dotted line for the y-axis. That's an important result, because what we're going to learn is that whenever you are looking at a moment of inertia, Any axis that passes through the center of mass is going to have the least rotational inertia possible. If the farther you move the axis from the center of mass of the system, the larger the moment of inertia is going to become. And that's a useful fact when we're looking at, qualitative questions and things like that. If we know where the center of mass is, if the axis is close to that, that's going to be a lower rotational inertia or moment of inertia than when the axis is far from that center of mass.